Our next example is problem 10.7 from Sturm 2010. It's at bank full depth for a stream in well-rounded alluvium with D50 equals 12 millimeters is 1.5 meters. The stream slope is 0.0005. The channel shape is approximately trapezoidal with 2-to-1 side slopes and a bottom width of 10 meters. Calculate the bankful discharge and determine whether the bed and banks are stable at bankful conditions. We will talk about the significance of bankful discharge in our next unit when we discuss natural channels. So in this example, it's a well-rounded alluvium. The normal depth is 1.5 meters at bank full, bottom width of 10 meters, side slope of 2, bottom slope of 5/10,000ths, and the D50 of the gravel is 12 millimeters. So first step would be to estimate the roughness using the predictive equations for Manning's N. So in US units, it's N equals 0.039 times D50 to the 1/6. In SI units, N equals 0.0475 times D50 to the 1/6. In the US, you would have to use it in terms of feet, and in the SI, you use it in terms of meters. And you'll notice that the two N values come out to be the same, which they should. Next, determine the area in the wetted perimeter. Since the normal depth is known, we can fairly easily compute the area and the wetted perimeter from the equations for the trapezoidal channel. We then compute the hydraulic radius of being 1.167 meters. Then, using Manning's equation, we will predict the bank full flow rate. So simply Manning's equation, as we've done many times in this semester, putting the numbers in, notice that the units constant for SI units is 1. The area, the bottom slope, it appears in this particular version that Manning's N has a 0 missing here. So remember, it was 5/10,000ths, not 5,000ths. So that's an error in the slide. That gives a bank full flow rate of 21.25 cubic meters per second. Then we would determine the critical particle size. First calculation to determine the critical particle size is to determine what's called the shear velocity, or the particle shear velocity. So U star is equal to the square root of G times the hydraulic radius times the bottom slope. So the shear velocity is 0.075 meters per second. We would then take that and put it into the Reynolds number equation to determine the shear Reynolds number. So that's U star times D50 divided by nu, which is the kinematic viscosity of water. The critical dimensionless shear stress, tau star sub C, we will use this time to be at the higher end and 0.056 from the modified Shields diagram. We would then put those values into the equation for predicting d sub C, which is called the critical particle diameter. So to determine the critical particle size, we evaluate the equation which we just mentioned, and you'll notice that comes out to be 6 millimeters. Now, to make sure we are applying this within the range of accepted values, we check to make sure that the hydraulic radius times the bottom slope or the friction slope is greater than 1.5 times 10 to the negative fourth meters. And as we can see, we match that criterion. Next is to compare the critical particle size to the particle size in the channel. So our calculated critical particle size, which we would expect to move, is less than the particle size, the D50 in the channel. So we will have stable banks. Now some of the smaller particles, which are less than 6 millimeters, will erode. Note that the larger values of the dimensionless critical shear stress give smaller values for the critical particle size.